OCR has already been done on it, and it's been done by Ebifine Reader. And character accuracy rate of that OCR is around 90–91%, which is clearly insufficient. So here I will show you one example of usage. So this is from paper of Alexi Vesanto and others from about 2 years ago. Here is this part enlarged so you can actually see what it says. So what they were trying to do is track how the news spread across Finland at that time in newspapers. And for instance, if a news was published in Helsinki, they wanted to see when and how it spread to the rest of the Finland. And here they actually identified a match of two same news published in two different places. But as you can see, OCR errors are actually making this task very hard for them. Of course, there are other examples of usage and problems that this poor OCR is causing. So when we started re-OCR or experiments how to do it, we decided to train models with Ocropy. And this was actually, I think, about 2 years ago that we started working on that. And we chose Ocropy because it's open source and it uses neural networks. And it's a whole package. So it contains tools for pre-processing, segmentation, training, recognition, and evaluation. And also it had really great results on the German historical documents. So at the time it was really I believe it was the best choice for us. For those of you who don't know the OCR workflow, so you start with a page image and then you can pre-process it. What we do is binarization. So we make images black and white. After that, images need to be segmented into lines to be fed into recognition that uses pre-trained model. And then you get, of course, text lines as output. We also did some experiments with post-processing, so you can do it afterwards. Since we already have OCR from Ebifine Reader, we actually don't do line segmentation. So we use existing line segmentation. That's kind of our master OCR. And that way, it's easier for us to compare the results, and also it's easier just to replace the existing results in a way, or like to have two different versions in a sense. And also because line segmentations of newspapers is so difficult, we just are leaving for somebody else to solve that problem for us, I guess. So the data, here on this graph, you can see there is data from 1820 till 1939 in blue. That's 4.6 billion tokens. We use all of that, and we also have some additional data from 70–71. So it's around 5 billion tokens, I would say, that we need to process. So it's quite a big amount of data. And the problem with this is that the texts are printed in two languages, mostly two languages, so Finnish and Swedish. And of course, there are other languages occasionally. And of course, there are two typefaces, Fraktur and Antiqua, all around. So now I will show you some examples of the data. So here, this is an example of scanned images of good quality. So this is Finnish Fraktur. I think this is extract from a priest's diary here. And of course, this is one column, so it's easy also for segmentation. This is an example of good quality Swedish Antiqua. So it has mostly two columns, but of course there are different segments on top and the bottom. Now this is one example of a newspaper with multi-columns, and this one is very hard for segmentation, both for ABI, and we tried also with Ocropy segmentation, so it's quite difficult. Here is this top enlarged, so you can see it better. And now this image, this is already binarized image. It also has challenging segmentation, but actually the problem here is that it has many fonts at one place. So the fonts are not separated across time or publications, but you can find many of them on one page as well. And here, this example shows that also on the same page, you can find multiple languages. So this is maybe like exaggeration because this is some kind of translation of Swedish into Finnish. But there are really real pages with some articles or advertisements in one language and some in the other language. And of course, there is a problem of poor quality. So here in this example, this is a binarized image, so we lost some data with binarization, which is maybe not the optimal way to approach this if the scan images are poor. Maybe it would be better to use grayscale in this case. And of course, after segmentation, we get line images. So here are examples of line images and ground truth, both in Finnish and Swedish, and this is for Fraktur. So although this is one type space, it has lots of different fonts inside of it. So there are different versions of Fraktur, and also the same applies for Antiqua. So what is our goal? That's to train a model that will be able to recognize everything. And maybe that's a bit ambitious. Well, we are still searching for an answer if that is possible, actually, or to recognize very well everything. Because it would be very hard with such a huge amount of data to kind of segment it into different languages or different fonts, for instance, and then separately do OCR on those. So we want actually a model to handle everything for us. In previous work, we did, so we tested Ocropy on Finnish data sets, and we applied post-correction with final state transducers. So we got character accuracy rates around 93.5 to 94.8%, and all our results improved slightly with post-processing. But what was important from these experiments was it proved really good to randomly sample lines from entire corpus. So instead of just having 250 pages and then get all of the lines from there, although that's 5 times more lines than these 10,000 lines from all corpus, we get this variety of font that from the entire corpus. And that way we need actually less data to train on to get good results. But also, because the corpus there is lots of Swedish material, now we wanted to add Swedish training data. So beforehand, we had 10,000 Finnish training lines randomly picked, and now we, the same way, randomly picked 6,000 Swedish training lines. And also, we did analysis on those lines to see how much Fraktur and Antiqua there were. So we found out that for Finnish, 75% of the randomly picked lines were Fraktur and 25% Antiqua, while for Swedish, it was around 50-50%. So we ran experiments. First, we wanted to see how much training data really is enough. And we trained Finnish model with 3,000, 4,000, and so on lines until 10,000. And the results are here shown in character accuracy rate and word accuracy rate. And we found that the best results are around 7,000, which was maybe a surprise because they'll always tell you, oh, when you use neural networks, you need as much data as possible. So when we were thinking what might be causing this, there are 2 possible reasons. One would be that we simply don't get more variety with more than 7,000 lines. So the model can't learn anything new. That was one theory. And the other theory was that since Ocropy has one-dimensional LSTM, that it simply can't, it doesn't have enough memory to remember everything. So that was the other theory. And I will tell you again right now that I think that was the true reason why this didn't work better with more data. So we did some other experiments. Now we used Finnish models. We trained them and tested on Swedish test sets, but now we divided test sets in on Blackletter and Antiqua. And also for Finnish test, we also did the same thing. So we divided it into subsets to see how it behaves on those subsets. And what we found out, of course, Finnish doesn't do very well on Swedish, which we knew from start. Here are results for Finnish, and we figured out that it actually does poorly on Finnish Antiqua, and that was the problem. So since there's only 25% of Antiqua in training, there simply isn't enough data to train on it. And Antiqua might have even higher variety of fonts than Fraktur. Then we did experiments with Swedish training data. So we have here two columns. One was Swedish trained on 3,000 lines, and the other one Swedish on 6,000 lines. And here, results on Swedish test set actually show that there is no significant difference on the results when models are trained on 3,000 and 6,000 lines, which was also surprising, but it comes as a previous result. We thought that we could train Swedish on 7,000 lines similarly like Finnish and get the best results, but actually Swedish saturates a lot earlier on 3,000 lines. And the surprising moment was that it does quite well, I would say, on Finnish Fraktur. It does the same as on Swedish Fraktur. Actually, the results are the same. So that also led us to conclusion that Finnish Fraktur is somehow easy, let's say, to recognize, or like it's possible that it's a good quality and there is not much variation. And finally, we did mixed models as well. So here we have Finnish whole data with Swedish 3,000 and Finnish whole data with Swedish 6,000. And we got better results when we mixed Finnish and Swedish 3,000. So on Swedish test set, it performs poorly in comparison to Swedish-only models. So it doesn't perform that well. But on a Finnish test set, we got the best results overall. So when we added some Swedish data, Finnish results improved. So this was maybe a surprise at first, but it is kind of logical, because if you look at results of Finnish Antiqua, so maybe I can show it here, they are the ones that actually improved. So by adding Swedish data, which has more Antiqua, that's the probable reason why Finnish Antiqua improves as well. So for future work, we definitely need more Finnish Antiqua for training. And also, since it's possible that one-dimensional LSTM has small memory, we would need to use deep neural networks. And the good thing is that future is already here, and we already did experiments in the meanwhile since we wrote this paper with calamari OCR. And so my recommendations to use it and try it, because it's really nice software. So it's actually a replacement for Ocropy's training and recognition evaluation. So you can use the same data that you use for Ocropy, you just feed it here. And it's really good because it's very powerful. You can define yourself the network that you want to use. And it has many other great features. One of them is it can be trained on GPU and recognized on GPU, which makes it very fast. So that's all for me. Thank you.
I have questions.
Can you explain why you binarized?
Well, that was kind of the way we found that it's done, I guess, at the time when we started doing that. So we looked at examples how other people did it, because we didn't have previous experience with OCR, and actually that was the reason. And what I think is that people maybe did it before because the neural network simply couldn't handle more information. There weren't enough memory. But I think nowadays with deeper networks, we definitely can use grayscale, or maybe even, I don't know, original image, I'm not sure, because we can simply process that data and have some use of it.
Maybe I just missed the information, but you were speaking of the size of your training corpus, with 3,000, 6,000, 7,000, and so on. How many training steps did you train for?
I will have to check, but it definitely depends on the size. So I think in the end, we did 1 million training steps altogether, but then from that 1 million on development set, we chose the best model. So, and I can't tell you right now I can't remember, but I think Swedish models were actually around 200,000 steps, the best models. and Finnish ones a bit more. Like I think the Finnish ones were like 500,000. But yes, this was, of course, this was a problem because it takes lots of time to train everything and then to test everything. And that's why Calamari is great again, because it has option of early stopping, so it stops when you don't have to train too much and then test it. So it tests automatically and stops on its own when it's done.
Any more questions? One more?
You said you wanted to train one model to see everything, or to OCR everything, because it's too hard to split the data into Fraktur and Antiqua fonts. Could you train another model to do the split, and then?
Yes, we were thinking about that. That's true. And also we have tools for language identification, and we could split by language as well. But the thing is, like, if neural network can do this work for us, then we would prefer that, because then it would be just faster to, because if we're working with such a huge amount of data, it would take simply a lot more time to have these different steps and effort. So if we could train a neural network to do it, to everything together, then that would be optimal. And I have to say, from this like future things, experiments that we are doing right now, I think we are going into the right direction, and I think it should be possible.
One last question.
Thank you. Was the incentive to improve driven by your users, or was it something that you wanted better quality data for because we were doing some language analysis on it? And also the second question, have you now re-indexed your new data? Have you finished processing, and is that now data you use publicly for search?
Right, so the answer is no. We haven't re-OCR'd everything yet because we wanted to improve it a bit more first. But I think that now that we are kind of getting, with Calamari, we actually got a few % more of accuracy. So we just have to, at one point, say, okay, now it's enough, and now we will reprocess everything. And then later, if it's still needed, then we can do something else to improve it further. But yes, right now, we don't have re-OCR. However, I'm approached by some people who are using that, and of course they would like to have the new OCR, so that's kind of a thing that should be happening in the near future, definitely, yes.
Thank you very much.